everybody. Last session. You're nearly there, but we have literally saved the best till last because I know you have questions about large language model technologies and how they work. Yes, you do. Don't say you don't. It was very revealing a moment ago in Chris's session where Chris said, of course, you all know how retrieval augmented generation pipelines work, right? And nobody went, actually, could you just go over that bit again? But anyway, here to give us an explainer is Daniel. Please give him a big, warm Teradata Possible welcome.
Hello, everyone. Good afternoon. I'm very happy to be here. I'm Daniel Herrera. I'm a developer advocate for Teradata. Been in the company about 2 years, quite a ride, and partly that's thanks to the confidence placed in me by Dr. Chris Hillman, so I'm very appreciative of that. And I'm very happy with my job here for one reason. I'm a developer advocate, so I get to explore all of the technologies that Teradata releases and ancillary technologies to those as well, because I have to explain to the market in general how you can make use of these in your organizations from a very broad perspective, top of the funnel, you can say, because everything that we create goes into YouTube, goes into blogs that everyone reads, not only Teradata customers. So I get a lot of fun on that. And of course, because we produce a lot of material, here is my blog. You can follow me there, and you can check all things tech, data, and Teradata. And also, if you have any questions after this talk, you can reach me in LinkedIn or Twitter, wherever you are and wherever you hang out the most. I also consider myself a problem solver and a very curious person. And that's what drove me to this topic. Everything got crazy about generative AI and what this ChatGPT was doing. But I, since I was little, wanted always to know how things were made. That got me in trouble sometimes with my mom when I broke some watches or clocks in the house. But most of the time, it was very satisfying understanding the underlying mechanisms of technologies. And that's what inspired this talk. It's an exploration that I did for a certain amount of time, trying to digest how this works. And I really like to share my knowledge. That's the reason I'm a developer advocate. So that's the reason this talk came about. The other part that is actually quite interesting is that knowing how these technologies work under the hood actually gives you a very nice perspective of what are the limitations, what these technologies are good at, and what these technologies might not be a very good fit, because there's a lot of machine learning that you can do without generative AI with a lot of the tools that we already have in Teradata, but also you can extract a lot of value from new technologies and the combination of new technologies with those tools. An interesting example is this, right? Like this was very famous a while ago. Basically, is not a criticism of the platform or the language model. The language model is working perfectly as intended on what it does. But it happens that large language models are not trained in specific characters. They are trained on words or tokens. So that's the reason that this came out. And one thing that I really grasped after researching a lot about where these technologies might not be given the right results was this little saying. I really want to have the chill to accept that generative AI has limitations, but I want to have the guts to use it where it actually delivers value. But the problem is to have the wits to know the difference. And learning how this works actually have helped me to do that. And at its core, this generative AI is based on language models. And language models are no more than systems that are trained to analyze, I wouldn't say understand, but to analyze human language and being able to predict patterns of human language or many languages. And we have actually been using them for a while. The text prediction in your cell phone, that's a language model. The translation tool that you might be using every day, well, I live in the Netherlands, and I'm not a native Dutch speaker, so that's something that I use every day. And of course, the newest and shiniest application, which is the chatbots, those are actually language models. But I really wanted to demystify this thing that this is something really, really new Well, this methodology is actually relatively new, but we have been using language models for a while already for different applications. What language models do is basically two things. Model words, and to model something is to understand, to have a representation of that something, and being able to find patterns of that something in relation to similar things, right? And the other part that these language models do, besides only modeling words, is modeling context. And of these two tasks, there is one that is relatively easier, which is modeling words, representing the words in some fashion that makes sense for analyzing and building a model of the different words that might be in a text. But modeling context is a little bit more complex and a little bit more difficult. And I want to invite you with me to build your first mental language model. And all the vocabulary that we have is, Mary had a little lamb. And let's imagine that this is all the vocabulary we have. And based on this vocabulary, we want our model to be able to predict what is the next word after we input one of the words that is part of our vocabulary. This is a very small vocabulary, actually. So this is actually quite trivial. And the solution that we came out is actually quite trivial. We are going to count each of the pairs, combination of words, of each of those words in the vocabulary with each other. And then to predict what is the next word, we are going to have a little statistical representation, which is just sort of an average, a conditional probability. And of course, in that scenario, if we input Mary, we have Mary appeared 2 times, Mary had and Mary went, and we have 50% probability that the next word will be had and the next word will be went. So as simple as that. That's a very simple kind of toy language model on a toy vocabulary. Is just what we call a bigram model. If we make the entire representation of that model on how it looks like, we have this matrix, which is our vocabulary against our vocabulary. And then we have the probabilities of one word following the other one in our vocabulary represented in each of the cells. And here you will see that if we input Mary there in the first row, we have 50% probability of had and 50% probability of went there. So very, very simple, quite trivial. How do you think this performs? Well, actually, building bigram models actually doesn't really perform very well. And this is a family of language models that is called n-grams. So as we model pairs of words here, we could model triplets of words or quartets of words. And we can try on that way to embed more context to figure out what is the next word that should follow a progression. But this has limitations because it might get to a point where embedding a little bit more context on our calculation will exponentially grow the number of probabilities that we have to track. And that's the reason it's very difficult to embed a lot of context in an n-gram. Have I seen n-gram models in production? I think I have. I'm not totally sure, but I think these model predictions for the next word in our text prediction in our cell phone might be based in some idea like this, because usually they lose track after after a certain number of words. Like saying there, I see it now, but I set a day to come to you, to your place, to the Netherlands, and the data is a bit greasy. Well, I don't know. We are data scientists. Maybe we have seen greasy data sometimes, so I don't know. But yeah. So this type of model is not really great. How these new generation large language models, what they have found is the secret sauce on how to represent context in a very creative way, in a very efficient way, and in a way that is quite performant. Yes, it consumes a lot of compute, but for the amount of context that they are able to embed in the model, they are doing it actually very efficiently. And for that, they have solved several problems. They have figured out how to represent the word in a very nice way, so the word representation itself contains a lot of context. They have been able also to, in each specific instance that the word appears in an input, embed that context in the model as well, in real time. And based on that very rich contextual representation of the word, they predict the next word. So I know in the past you might have seen a representation of this diagram that looks a lot more complex. This, basically what is in the screen right now, is a very summarized and consolidated version of a transformer, which is the core of the large language models that are in vogue these days. But I cut only the more important aspects that are very easy to understand conceptually and that will give you a very good idea on how this technology works. Of course, there are other details that I'm not covering in this talk that are related more to the neural networks that are used to train a model. That is out of the scope, but I have a surprise at the end of the talk for the more technical of you, and I will show you when we get to there. So first step, what and where is the word? What is our word representation? So let's make a little exercise right now. Let's think in the word tiger. And then let's try to make a mental map of what are concepts that might be related to this word, tiger. One is that it's big. One is that it's, of course, it's a feline. There's something weird there, right? Canine. Why canine? It's a tiger. What does it have that is canine? All carnivores, all predators have canine teeth, which is the ones that are used to basically cut the meat, right? So we have canine as part of the concepts that are related to tiger. Now, let's imagine that for each of these concepts that we have defined that are related to the word tiger, we can add a quantification. So we have one column for size, we're going to give it an 8. One column for feline, we're going to give it an 8 as well because it's very big and it's very feline. It's not a lot of canine because it's only the teeth that are canine, so nothing else. This, in summary, is what an embedding is. I know the data scientists here will like to kill me because that's not exactly what it is. But I'm building a mental map for this. We actually don't know what each of the columns in the embedding actually means, as clear-cut as I have put it here. But this is offering a very good mental map to tell you that each of these columns in the embedding represents something. Maybe it's something that only the model itself knows. But this is a very useful mental map because at the end, the model is doing something very similar to this. Now, imagine this quantification, you have already built it. Now that you have that, you can perform certain interesting operations on top of it. Let's say that in one operation, we are going to perform a subtraction. We are going to extract a lot of the size only and leave everything else equal. So we will get from this representation that we had at the beginning that was a tiger, we are going to get something else there. Can you guess what would be that we're getting there as a result? Anyone? Not really. Anyway. Exactly. It's a cat. It's not very big, only 2 in size, but it's still very feline, and it has canine teeth. Now, let's do other addition, subtraction there. We're going to subtract a little bit of size. We are going to subtract all the feline, but we are going to add a lot of canine. What is going to be the result? Yeah, exactly, a wolf, a dog, an animal of this kind. So as you see, this representation of embeddings can do these kind of operations. And this is something that you can do if you look for any embedding library in the internet. You can do it yourself. If you have the concept of king and you subtract the embedding of men, the result is going to be the embedding of queen. So they are able to contain this amount of context about what the word is. And this is more very similar, kind of like the features are actually not exactly what embedding contains. It's just an illustration. But these operations will give you actually results very similar to this. Other thing that you can do once you have these embeddings is that you can know what concepts are close to each other. And for this, we need to perform certain mathematical operation. But let's demystify that one as well. You have heard of it if you have watched videos or read papers or documents about large language models. You have heard about that product. And that product is nothing more than multiplying each of the columns of the embedding and then adding them together. And that will give you a number. And the bigger that number, the more neatly related or closely related these two concepts are. So, for example, we have the tiger embedding, our toy embedding here. If we perform the dot product operation on the cat embedding, will give us a very high number. That means that cat is actually quite similar to tiger. If we do the cat embedding, which we have over here, against the wolf or big dog embedding that we have over there, will give us a much lower result of the dot product. That means that those concepts are not really related. What this means is basically that we are able to relate concepts with a number. We know exactly if two concepts are very close to each other or far away from each other. Illustrations that you have seen about this is what Dr. Hillman presented before with Sasha. When you are doing a semantic similarity of text, this is what is happening. It's making a distant measure between those representations, and the ones that are similar have a very high value for that, and you find which ones are close to each other. Now, basically, what you will end up having, and we are going to go from our toy example to an actual model right now, we are going to have a matrix that will have all the words in our vocabulary. Let's say that we have 128K words in our vocabulary. And let's say that we are going to have a little bit more than 4,000 features, like for these columns that we're representing certain things regarding the concepts. And that is a word embedding matrix, which is the beginning of the large language model architecture or of the transformer. This is the starting point. We are only in the starting point. I hope Alba doesn't kill me. Let's go for the next step. Getting the context from the surrounding words into a specific word. And you might be thinking, well, the embedding already has a lot of the information about the word. What are the concepts that are related to it? Is very nicely quantified. Why we cannot use the embedding directly to build our probability distribution of what is the next word that we are predicting, which is what our language model wants to do as its main task. Well, the reason that we cannot do it directly or on the embedding, and that is not really recommended that we do it that way, and that it will not perform very well that way, is because different words have different meanings on different contexts, even when they are exactly the same word. So we have here a Python ate the mouse. That's a sentence. And for us as humans, it's very easy to know, yeah, Python ate the mouse is talking about a snake and a mouse, and the Python ate the snake. Control your mouse with Python. Totally different context, but the same word. And as it happens, the original word embedding of each of these words contains sort of an average of what concepts are related to this specific word. So it wouldn't know if we are talking about Python as a programming language or Python as an animal. It contains, that embedding contains the information for both. So we need, in order to make predictions, to know what is the specific context in which the prediction is being made, to know whether we're talking about an animal or a tool, which is a programming language. And the important thing here is that words have gravity. The context of the word might be able to pull that original embedding that we have for Python or mouse towards certain coordinates. So we have only two dimensions of our embedding represented here in the graph. We have the dimension of, we have the animal and tool feature. And in the case of the first sentence, a Python ate the mouse, we see that the presence of the word ate is adding a lot of animal to the word Python and adding a lot of animal to the word mouse, and is subtracting from the tool concept from both of them. So it's pulling them closer to being animals. In the case of the other sentence, is doing the opposite. It's adding a lot of tool and subtracting the animal by the presence of the word control. This is kind of like a very high-level presentation on what this transformer is doing, but let's get into the details on how is it doing it, because that's the interesting part. Let's imagine that for each of the words in our input, which is our sentence, we have a table. We have three different types of tables. One table is telling for each of those words what these words are looking for. And we are talking only of our text input in this case. And for each of the words in our input, we have also another table that is telling what each of those words is offering. What am I as a word? And then what I contribute as context. That's the third one. So if we have this in our mind, we can see that Python is asking for, being a noun, is asking for verbs, wants to know verbs around it. The word ate is a verb, so in its key matrix, which is what we call the matrix about what the word is offering, it's offering a lot of verb. And by our dot product, we know that if they are very aligned, they are going to kind of have a very high value there. And this value, because it's going to be very high, will add a lot of the context that that specific word is adding to other dimensions, in this case, to the dimension of animal. So basically, we have each word is asking, hey, I'm this type. I'm looking for this other type. How much do you have of that? And what you can offer me when we match together. And in this case, we have this verb ate offering a lot of animal. In the case of the other sentence, we have the verb control offering a lot of the dimension of tool. So this is a little bit more in detail on how we manage to make the words have gravity. Now, this is the secret sauce, or how they are making this to work. During training, the model discovers certain matrices. The model discovers a matrix for generating queries, a matrix for generating keys, and a matrix for generating values. These are not input by anyone. This is by brute forcing on all of the data. The model is learning about these matrices. There is an operational, there is a mathematical operation that these weight matrices, as we call them, go through when they are multiplied by the original embeddings that we have. That will give us the Q, K, and V matrices that we were mentioning before. So that will produce the original embedding we have at the beginning, which is discovered by the model as well as it trains. We have three weight matrices that are discovered also by the model as it trains. And when these two are multiplied together, we get our matrices that we can use during inference to get the context and get the words to have gravity. As mentioned, when a query and key, so what the word is looking for, matches very well to what other words are offering, they are aligned, and they will give you a very high value. And this value is what we call an attention weight. This value is the one that multiplied by the value matrix that is also that we created according to the process that we described before, will give us the attention results, which is another matrix that's getting repetitive at this point. But this attention result is only representing our prompt, if you want to visualize it this way. It's only related the words that we put in our input. And that's what we get at the end of the transform of the attention mechanism. So what you can remember at this point is attention means only that the words are paying attention to what other words are in their own context at the moment that the user puts the prompt. And they are doing it through this process that we discussed. We have to get from that attention result to what is the next word that needs to come after. And the matrix that we need to make that prediction, the final result that we need to actually make a prediction of what is the next word, is going to look something like this. A Python A the, and for the last word the, we want to know the probability of what is the next word that follows. And you can imagine that we have n words in our vocabulary, whatever, and these are the only ones that have values. And of course, we're going to pick the highest one of those. That's not necessarily the way it works. Usually, they have a bag of probabilities, and they kind of like randomly select the ones with the highest probability, so it doesn't become so robotic when it answers, but that's a detail. Let's say that we just pick the highest probability. And of course, for our other sentence that we have, it's going to be, the probability is going to look a little bit like this. But if you remember what we had at the end of the attention mechanism, we have each of the words in our input, but we don't have probabilities. What we have is the attention values, right? The attention result that we have. So we need to go from that attention result to this matrix of probabilities. And if you are guessing, we are going to multiply by another weight matrix to get that. Yeah, you're right. So we have, this is what we were talking about. We need this type of matrix to make predictions. But we have this, the attention result, which is just our words in our input plus the value in the features according to what was the result of the attention. And multiplying this attention result by another matrix that is called the output weights, you get the matrix that we need to make the predictions. So it's, again, a matrix multiplication operation that allows us to go from where we were to where we need to be. And these attention weights, these output weights, are also learned during training. So as a summary, and I think I'm almost there, for getting this, we have gone to the following steps. We need a representation of the word, which is the word embedding. Part of the story that I didn't tell you is that the attention mechanism works in parallel. That's one of the reasons it's very efficient, but that means it doesn't have idea what words came first and what words came after in a specific collection of words that we're sending as inputs. So we encode the position of the word, adding some values to the word embedding. But I didn't cover that because it's not, it's something that can be explained at the end. but think of the word embedding as just the representation of the word. But the position is actually put inside the word embedding at the beginning as well. Then we go through the attention mechanism, where what I want you to take with you is that the words have gravity. So we want each of the words in the input to exert certain gravity on all the other words in the input, and that will give us a very rich contextual representation to make our predictions. Let's touch on that one later. Then, after we have the attention result, which is our words in our input and the value that they have according to all of the features, we can produce our probability distribution, which we get from the output weights. So all of these matrices that you have here, these are learned during training by the model. So basically, by going through all the data that you are training the model on. For closing, I really like this quote from this professor, and right now working in Meta. And I want to summarize it this way. LLMs cannot answer questions whose answers are not in the training data. This is key. LLMs cannot acquire new skill or knowledge without human intervention, and this, I think, is also key. As you see, they are just predicting the next word by a very rich contextual representation. And LLMs cannot invent or create. That's a human activity. This is kind of like a philosophical point, but I really believe it. And according to how they work, I think that's a very correct statement. Now, there are very interesting use cases that you can have with this technology, specifically with embeddings. I think the chatbots are very interesting, but I think the most value that enterprises will get out of this technology comes from this. 85% of the data in the world is unstructured. It's in the form of text that doesn't have any tabular representation. It's not a structure. It's not JSON either. It's just text, like emails and stuff like that. It's videos, it's audio, it's everything that is unstructured. And by applying embeddings to this unstructured data, we can come to what Martin was mentioning before. You can have other type of features that enrich the data that you already have. And that can unlock a lot of value for your organization. And you can do that with us in Teradata. We have several ways that you can interact with large language models in our platform. You can do it inside the database. If you have a small language model that is small enough, you might be able to do it inside the database itself through importing an ONNX file and bring your own model technology. You need a little Java library there, but that's a talk with us if you want to explore that use case. We can walk you through it. In platform, this is our new bring your own LLM technology, where you can bring any model that you have on Hugging Face that is up to a certain scale, and you can bring it in thanks to Open Analytics framework, and you can create your embeddings there as well without having to do an external call. And in the last case, even if you need to use one of the models from the CSPs or from companies like OpenAI, we have API-based integration to those models. To close, for those more technical of you that want to continue exploring, you can scan the QR code there. That's a repository where I walk you through how to create your own large language model that can write kind of like Shakespearean English. If you are doing on CPUs, this really doesn't get very nice results, but it does create something that's similar to words. But it's very interesting if you want to explore how the neural network works and how these models are trained. All of these details that I omitted in the presentation, you can get it there. This is a fork of a repository for Andrej Karpathy, but I did some modularization there that allows you to kind of like tweak it to your needs a little bit easily. And of course, for exploring LLM use cases, you can go to ClearScape Analytics Experience. We have some embeddings already downloaded in the environment in our object storage, so you don't have to generate them yourself, and you can see what you can do with embeddings. So that will be all for my presentation. Thank you very much for your attention.
Thank you, Daniel. It looks like magic, but actually it's matrix maths and probability distributions, and that was a really clear explanation of how it all works under the covers. So thank you very much for that, for Daniel. Have we got any questions from the audience for Daniel on any of that presentation? This is always the moment, isn't it? It's the end of a long day. Oh, we have got one question.
The examples you gave were very nice, very simple, but I suppose in the real world, how do these scale? So we know that part of the problem is that in order to be accurate, as humans might interpret it, they need a lot of data. And what sort of sizes of sets of vectors are needed for ChatGPT and these kind of things?
Oh, that's a very interesting question, and it's something that I didn't talk in detail, but it's here, actually. There are two things that the transformer does to scale nicely. And both of them are related to the fact that when you are training, on the training step, which is where you are kind of brute forcing a lot of the data, you can chunk different batches of data, different batches of text of different size. It's not done on words, that's just my example, it's done on tokens, which are very similar to words, but not necessarily the same. And each chunk of words is interpreted as an input. When you are on inference, the only word that matters is the last word in the sequence, right? Because you want to predict what follows that one. But during training, you have an entire chunk of words. Let's say that you have 18 words, for example, 18 tokens. You can predict, you can get your model to have some inference or making the training on what is the token that should follow the first one, what is the token that should follow the next two. So basically, in one batch, there can be a lot of predictions already. And all of them can go in parallel because the model doesn't care of the order that the words came about. And also, when they are producing these matrices that we have here, is not only one weight matrix for queries, one weight matrix for keys, one weight matrix for values. They split the entire embedding space into several heads, they call it. And each of these matrices is a little bit smaller than the entire embedding space and focus in only a section of the features. Then when you do your training, you are doing the training with different versions of these weight matrices that can also work in parallel. And it gives you another interesting feature is that you allow these words have gravity concept to go from having only one perspective to having as many perspectives as heads of attentions you have. And then they stitch everything together at the end, which is another story. But yeah, a lot of the scaling comes from these properties of the transformer model of being highly parallelizable, which is something that previous language modeling techniques didn't have. Like when you have the recurring neural networks, it could not be parallelized because they have to keep a memory what came before. This one doesn't. This one can go all in parallel because the position is encoded on the embedding as part of the first step. Of course, it's still a lot of data, so you need a lot of GPUs and a lot of energy, but that's another discussion.
Thank you.
Any other questions? There's one here at the front, I think.
Thank you very much for a presentation on a very complex concept. I noticed the word transformer, and I don't know whether I missed it or not. So basically, in this context, it's a transformer model
Yeah.
or not, number one. So I think that my question is that for business, I'm a business person. So from a business standpoint, there's always a very fundamental decision on whether you build your own or you use pre-trained model and to really repurpose it, decision to buy or to rent or to build. I wonder whether you have any insights on how to go about that question, because it's definitely very complicated, very technical.
I have an opinion, but you go first, Daniel.
Yeah, I have an opinion too. I think we will have similar opinions, but let's see. I think you don't have to train your own. There are a lot of very nice quality open source models already available. And also for your use case, you might not need to have a model with a lot of features, which is what we have here, right? Like this one that we have here with a 4,000 something, like this illustration over here. You might need something that is a lot smaller than this to just generate certain embeddings to find for similarity in your data and a little bit like that. You might find an open source model that's already on a smaller size that you can use, and that will be cheaper, and you can deploy it in Teradata if you are already a Teradata customer, and that will be even more convenient and more proficient. I think it's not one size fits all, but I do think if you are not OpenAI, and if you are not kind of like trying to mimic a lot of human intelligence, but you are trying to put a structure on a structured data, you might not need a huge, super, super big model. You might need something small to mid-size that you can get from the open source community, maybe do a little fine tuning afterwards if you have a very specialized use case. Many cases that wouldn't be even necessary. Matt,
I mean, yeah, completely. I think in this particular space, I don't think there's any value in attempting to train your own model. I think there will be some use cases, and I guess we touched on this earlier when in Chris and Sasha's presentation with Martin. There will be some cases where it might be worth fine-tuning some of those models, but you're not going to do better than the open source community in this space. I think, you know, I made a deliberately provocative statement this morning during the keynote when I said that our competitors who were training their own large language models were guilty of vanity projects. And yeah, I'm being a little bit provocative, but I also agree. They're not going to do better than the open source community is already doing. And it's, in my opinion, a waste of shareholder capital. You know, the job is to be able to import the open source models where they're appropriate and to be able to connect with the foundation models through API integration. That's my personal opinion. That's how it looks right now. If you think about particularly the foundation models, if you think about the time, trouble, expense, and expertise you need already to be in that game, it's a very small club. Very small club. And the diminishing returns, I think, with the current approaches mean that you know, very few people need to apply for membership of that particular club. Yes, of course, yeah. And fine-tuning, I think, might be a thing for domain, or is a thing for some domain-specific applications as well. But fine-tuning is very different from writing your own from scratch.
We have time for one more question.
Right. One more question if there is one, Alba says. We have time for one more question. Going once, going twice, going 3 times. Well, I have one thing to say, but before I say it, let's thank Daniel one more time. Thank you very much.